file IO buffering. That is exactly where I'm at. 13.5. So this is the main kind of diagram in the reading that I did off stream. Just to recap, so the user is interacting with glibc. It maintains its own buffers for its calls, its IO calls. And then once its buffers fill, or once, I think when you hit like a new line character on some files, it'll flush the buffer. Do write syscalls, and the write syscalls are then buffered. It says kernel buffer cache, but apparently from the reading, apparently these are basically just like the kernel's page cache. Yeah, there's not like a separate kernel file buffer cache. Kind of reuses the same page cache as everything else. And then once these kernel internal buffers fill up or are flushed, then it actually does the writes to disk. And there's different types of writes. I guess that's another thing that the reading covered is you can have different types of syncs here. So fdatasync basically says sync only the data. fsync says sync the data and all the metadata associated with it. So like modification time, stuff like that. And then I think there's this syscall that you could do to sync ranges, which I think is maybe the sync call. Fsync, fdatasync, sync. So sync, I guess, is kind of similar to fsync, except fsync is tied to a file descriptor, whereas sync is not. Which makes sense from the naming. And then there's also like when you do an open syscall, you can pass in the flag osync, which means that basically all the kernel writes will get synced out immediately to disk. And then they're talking about how sometimes when you're syncing, it just sends it to the disk's controller memory. It's not actually persisted onto like the platters or whatever if it's a mechanical hard drive. So yeah, you're not necessarily guaranteed that the data is persisted, is durable, but you're certainly more guaranteed than if it's stuck in a kernel buffer cache or glibc buffer. Yeah, flush clears the buffer in glibc, and then you can also say, hey, set the buff on this stream to null, and then disable buffering as well in libc. So that's pretty much like a TLDR of the reading that I did off stream. All right, let's dive into the next section here, advising the kernel about IO patterns. The POSIX fadvise system call allows a process to inform the kernel about its likely pattern for accessing file data. There is a fcntl.h syscall POSIX fadvise takes in the file descriptor, an offset, a length, and the advice. The kernel may, but it's not obliged to use the information provided by POSIX fadvise to optimize its use of the buffer cache, thereby improving IO performance for the process and the system as a whole. Calling POSIX fadvise has no effect on the semantics of a program. The FD argument is a file descriptor identifying the file about whose access patterns we wish to inform the kernel. The offset and length arguments identify region of the file about which advice is being given. Offset specifies the starting offset of the region, and length specifies the size of the region in bytes. A length value of 0 means all bytes from offset through the end of the file. In kernels before 266, a length of 0 was interpreted literally as 0 bytes. The advice argument indicates the process's expected pattern of access for the file. It is specified as one of the following. POSIX fadvise normal. The process has no special advice to give about the access patterns. This is the default behavior. If no advice is given to the file, Linux, this operation sets the file read ahead window to the default size of 128 kilobytes. POSIX fadvise sequential. The process expects to read data sequentially from lower offsets to higher offsets. On Linux, this operation sets the file descriptor read ahead window to twice the default size. POSIX fadvise random. The process expects to access data in random order. On Linux, this option disables the file read ahead. POSIX fadvise will need. This process expects to access the specified file region in the near future. The kernel performs read ahead to populate the buffer cache with file data in the range specified by offset and length. Subsequent read calls on the file don't block on disk I/O. Instead, they simply fetch data from the buffer cache. The kernel provides no guarantees about how long the data fetched from the file will remain resident in buffer cache. If other processes or kernel activities place a sufficiently strong demand on memory, then the pages will eventually be reused. In other words, if memory pressure is high, then we should ensure that the elapsed time between the POSIX fadvise call and subsequent read calls is short. The Linux specified read ahead system call provides functionality equivalent to POSIX fadvise will need operation. POSIX fadvise don't need. The process expects not to access the specified file region in the near future. This advice advises the kernel that it can free the corresponding cache pages if there are any. On Linux, this operation is performed in two steps. First, if the underlying device is not currently congested with a series of queued write operations, the kernel flushes any modified pages in the specified region. Second, the kernel attempts to free any cache pages for the region. Hold on, let's go back. First, if the underlying device is not currently congested with a series of queued write operations, the kernel flushes any modified pages in the specified region. Second, the kernel attempts to free the cache pages for the region. For modified pages in the region, this second step will succeed only if pages have been written to the underlying device in the first step. That is, if the device write queue is not congested. Since congestion on the device can't be controlled by the application, an alternative way of ensuring that the cache pages can be freed is to precede the FD fadvise don't need operation with a sync or fdata sync call that specifies FD. So you flush everything, or synchronize everything, I should say, and then immediately call this don't need, so it doesn't read those sections. Eagerly into any type of buffers in the future. POSIX fadvise no reuse. The process expects to access data in the specified file region once and then not to reuse it. This hint tells the kernel that it can free the pages after they have been accessed once. On Linux, this operation currently has no effect. The specification of POSIX fadvise is new in Subsp 3, and not all Unix implementations support the interface. Linux provides POSIX fadvise since kernel 2.6. Bypassing the buffer cache, direct I/O. Starting with kernel 2.4, Linux allows an application to bypass the buffer cache when performing disk I/O, thus transferring data directly to user space to a file or disk device. This is sometimes termed direct I/O or raw I/O. The details described here in the Linux specific are Linux specific and are not standardized by SUSV3. Nevertheless, most Unix implementations provide some form of direct I/O access to devices and files. Direct I/O is sometimes misunderstood as being means of obtaining fast I/O performance. However, for most applications, direct I/O can considerably degrade performance. This is because the kernel applies a number of optimizations to improve the performance of I/O done via the buffer cache, including performing sequential read-ahead, performing I/O in clusters of disk blocks, and allowing process access the same file to shared buffers in the cache. All of these optimizations are lost when we use direct I/O. Direct I/O is intended only for applications with specialized I/O requirements. For example, database systems that perform their own caching and I/O optimizations don't need the kernel to consume CPU time and memory performing the same tasks. We can perform direct I/O either on an individual file or on a block device, e.g. a disk. To do this, we specify the oDirect flag when opening the file or device with open. The oDirect flag is effective since kernel 2.4.10. Not all Linux file systems and kernel versions support the use of this flag. Most native file systems support oDirect, but many non-Unix file systems, e.g. VFAT, do not. It may be necessary to test the file system concerned. If the file system doesn't support oDirect, then open fails with the error E invalid, or read the kernel source code to check for this support. If a file is opened with oDirect by one process and opened normally, i.e. that the buffer cache is used by another process, then there is no coherency between the contents of the buffer cache and the data read and written via direct I/O. Such scenarios should be avoided. The raw 8 manual page describes an older, now deprecated technique for obtaining raw access to a disk device. I'm curious. Sorry, there's a lot of noise going on because they're installing a railing upstairs on my patio. I'm curious. I thought there was some type of coordination between opening multiple files for write access. Is that not the case? I wonder if I create multiple processes that open the file and do random writes with lseeks, if that would result in like concurrency issues. Let's launch AI real quick, and we're just gonna say, hey, write me a simple C program that opens a file in temp, a file, we'll just say from the first positional argument, and then holds the file open for ever, performing lseek to 0 offset and writing a string of characters the same character repeated multiple times. We'll say 4096 times. The character will be provided as the second argument. Let's jump over to chapter 13. Oh, we don't have a chapter 13. Oops. AVZCI, chapter 12, into here. It's RM uname star RM12 star Vim clang D, make this 13. Make clean, vim make file. That should be fine. Build. Let's build zig. Okay. Let's do LT N9 ref. Not N. What is it? T? No. L9. There we go. So you don't want ref syslimit. There we go. We'll just say this is gonna be concurrent file rights dot c. Grab the code, fix this, argc, printf standard error. Yeah, that's fine. File char. argv20 is the char. Then we open write only create. Yeah, that's fine. 644 fd. Yep. Character 4096. Then we say, hey, memset all that, and then forever. Yeah, let's not slow it down. lseek to offset 0. What is off t? What is this thing? Huh? Oh, no, it just says if the offset is negative, that's a cast. Then we error that out, else we write, and then we error that out. Let me just do that forever. Okay, looks exactly what I wanted. This is complaining that we don't need standard lib or error no, which seems like we don't. And then if we go in here, say make, build, current file rights. We'll do it on temp A, and we need character 1. And then if we do another terminal here, jump to chapter 13. If we tail temp A. Okay, just a bunch of 1s. And then we're gonna run build concurrent file rights temp B2. And then finally we're gonna create another terminal here, and we're just gonna cat out temp A. Why is it? While true, cat temp A, and then we'll say in shell, how do you unique all characters in a file? Oh, there's a fold W1 from standard input sort unique. Oops. Done. While true, do that. And then we'll say last is equal to empty string. We would say new is equal to this, and then we say if then phi. So we say if $new is equal to last, then we do nothing. But if it's not equal to last, then we're gonna have to do last is equal to $new and echo $new. Phi done. Huh. Cat. Oh, I did temp B. That's why. That's so dumb. All right. I don't know why I did temp B here. Okay, there we go. There we go. There we go. Cat temp. Oh, interesting. We get some that have 1 and 2. So you get partial rights. That's what that's saying there. So if you do a cat attempt A, oops. I'm gonna do full screen on this. We might catch one. Yeah, there's a partial here. All right. So we have verified that. So there's no, like, when you open for writing, you can just be writing. You could be racing with other things that are writing. There's no, kernel has no problem with you doing that. All right. Alignment restrictions for direct I/O. Because direct I/O on both disk devices and files involves direct access to the disk, we must observe a number of restrictions when performing I/O. The data buffer being transferred must be aligned on a memory boundary that is a multiple of the block size. I need to put my phone on do not disturb. Otherwise, I'm going to be distracted by these things going off. Turn on, bam. Okay. The data buffer being transferred must be aligned on a memory boundary that is a multiple of a block size. Guess that makes sense. The file or device offset at which data transfer commences must be a multiple of the block size. Okay. The length of the data to be transferred must be a multiple of the block size. So the length of the data, the alignment of the data, and the offset of the device or file all need to be multiples of block size. Failure to observe any of these restrictions results in an error invalid in the above list block size. Means the physical block size of the device, typically 512 bytes, when performing direct I/O, Linux 2.4 is more restrictive than Linux 2.6. The alignment length and offset must be multiples of the logical block size of the underlying system, typically file system logical block size are 1024, 2040, and 4096. Example program. Listing 3.1 provides a simple example of the use of ODirect while opening a file for reading. This program takes up to 4 command line arguments specifying in order the file to be read, the number of bytes to be read. Okay. This is all direct IO. Mixing library functions and system calls for file IO and summary. I'm not a huge fan of like file IO. It's like kind of boring. Okay. The program takes up to 4 command line arguments, specifying in order the file to be read, the number of bytes to be read from the file, the offset to which the program should seek before reading from the file, and the alignment of the data buffer paths to read. The last 2 arguments are optional and default to offset 0 and 4096 bytes respectively. Here are some examples of what we see when we run this program. The direct read. Okay. Programming listing 13.1 uses the memoline function to allocate a block of memory aligned on a multiple of its first argument. We describe memoline in section 7.1.4. I don't even remember reading about memoline. So much information. 7.1.4. Let's see. Let's see. 7. Other methods allocate memory in the heap. Calloc and realloc. Here it is. The memoline and POSIX memoline functions are designed to allocate memory starting at address aligned to specific power of 2 boundary, a feature that is useful for some applications. Memoline function allocates yeah. Okay. I guess maybe I just glanced over it. Okay, okie-dokie. I don't really care about this program, to be honest. Boop. Mixing library functions and system calls for file I/O. It is possible to mix the use of system calls and the standard C library functions to perform I/O on the same file. The file no and fdopen functions assist us with this task. Okay, so the file no, you give it the stream, the file stream, it returns a file descriptor. And then fdopen gives you back, or you give it a file descriptor and it gives you back the file stream. Given a string, file no returns the corresponding file descriptor, i.e. the one that the standard IO library has open for the stream. The file descriptor can then be used in the usual ways with IO system calls such as read, write, dupe, and fcntl. The fdopen function is the converse of file no. Given a file descriptor, it creates a corresponding stream that uses this descriptor for its IO. The mode argument is the same as for fopen, for example. Sorry. R for read, W for write, and A for append. If this argument is not consistent with the access mode of the file descriptor fd, then fdopen fails. The fdopen function is especially useful for descriptors referring to files other than regular files. As we'll see in later chapters, the system call for creating sockets and pipes always returns the file descriptor. To use the standard IO library, With these file types, we must use fdopen to create the corresponding file stream. When the standard IO library functions in conjunction with IO system calls to perform IO, it's kind of interesting. When using the standard IO library functions in conjunction with IO system calls to perform IO on disk files, we must keep buffering issues in mind. IO system calls transfer data directly to the kernel buffer cache, while the system IO library waits until the stream's user space buffer is full before calling write to transfer that buffer to the kernel buffer cache. Consider the following code used to write to standard output. Printf, to man the world is twofold. Right. In accordance with his twofold attitude. In the usual case, the output of printf will typically appear after the output of write, so that this code yields the following output. The intermingling of IO system calls and standard IO functions judiciously use of flush may be required to avoid this problem. We could also use setvbuff or setbuff to disable buffering, but doing so might impact IO performance of the application, since each output operation would then result in the execution of a write system call. Substitute 3 goes on some length specifying the requirements for an application to be able to mix the use of IO system calls and standard IO functions. See the section headed Interaction of File Descriptors and Standard IO Streams under the chapter General Information in the System Interfaces XSH volume for details. Summary: buffering of input and output data is performed by the kernel and also by standard IO function, standard IO library, glibc. In some cases, we may wish to prevent buffering, but we need to be aware of the impact this has on application performance. Various system calls and library functions can be used to control the kernel and standard IO buffering and to perform one-off buffer flushes. A process can use POSIX fadvise to advise the kernel of its likely pattern for accessing data from a specified file. The kernel may use this information to optimize the use of the buffer cache, thus improving IO performance. The Linux-specific open O-direct flag allows specialized applications to bypass the buffer cache. The file no and fdopen functions assist us with tasks of missing syscalls and standard C library functions to perform IO on the same file. Given a stream, fno file no returns corresponding file descriptor. Fdopen performs a converse operation, creating a new stream that employs a specified open file descriptor. Boop. Further information describes the implementation advantages of buffer cache on system V. Rationale of implementation system V buffer cache. Further information. Further relevant information specific to Linux can be found in so and so. I'm good on that. Okay. Let's have some fun here with these exercises. Okay, let's go here. We're getting, sorry, 4.1 copy C. Let's go back to chapter 4. Make, build, CD into build. There's a copy here. Copy. Boop. mkdir file IO. wget that guy. Wait a minute. Shouldn't that be there? would expect this to build that program, but it's clearly not doing that. Oh, get status. Yeah, the file's already there. And it did build it, but I didn't go into the file IO directory. Copy. LSLA build file IO. Why is that there? Should be under ref file IO. Yeah. Make clean. Make build ref file IO. Copy. There we go. So we want to time this thing. Come on. What are we doing here? Experiment with different file and buffer sizes. Set the buffer size by using debuff size. I don't really care about file IO. Alright. I feel like a zombie right now. Like I don't want to do any of this stuff. I just don't get the value of doing this. And it's a lot of work. I'm gonna go get some more matcha because I just don't have the brain power right now to get through this. I'll be right back. Play some music while I'm gone here. So one thing that I'm curious about is if this buff size declaration or definition or whatever they call it, macro pound define, um, if that thing is specific to his program or is it something that's generic for libc or what? So I'm going to go in and look at the source code for this. It looks like it is something that he defined here. Okay, that makes sense. So by default, it's 1024. So what we'll do is I just want to automate this whole thing. So temp, let's see. We're going to be copying some files. Experiment with different file and buffer sizes. So let's mkdir under temp. We'll call it copy files, and we'll cd into there, and we'll cat out dev u random. Let's see here. So ask AI. How do I guess I can use dd? Yeah, I can use dd input file. I think it's if is equal to dev u random, and output file is equal to temp. Copy files, we'll say 10 megabytes, and in here we'll say bs is 1024. I think that's how many bytes. That's k. Can I just say 1 megabyte, and then the count is equal to 10? Okay. And it's MIBI bytes. Okay. And if we do ls-la here, ls dash so if we do divided by 10 and then divided by 1024 should get 1020. Okay, good. So that's MIBI bytes. So that's a 10 meg file. Let's do a 1 meg file. 1 megabyte. We'll do 100 megabytes. I think those are enough. 110, 100. I don't think we need to get a gigabyte going here. And if we head like 100 megabytes, you can see it's just a bunch of random data. Cool, cool, cool. Okay, so we have our test files. Now we want to experiment with different buffer sizes. You can set the buffer size when compiling a program. So I'm going to go jump over to chapter 13. And then here I'm going to just write a script called test copy.sh bin bash, and we're going to say our quit, right quit. I'm going to grab this stuff here, and I'm going to say vim create function create copy files, and then here, oops, say for x, or say I in 1, 10, 100, do echo $I done. Comment this thing out, and this is going to go in here. But I want to make sure my loop is right. And then here I'm just say function main is going to be running create copy files, and we'll just call main there with $at. And we'll say change mod plus x test copy, and then we'll just run that. Gets us all of our things. Can I say 1m here? 1m, 10m, 100m. Does that work? Yep. So then here will be our, we'll call it $size. And we'll do size for size in there. dd uran, we need to mkdir under temp copy files. That looks okay to me. So if we ls-la temp, actually, you know what we'll do with rm-rf temp test or just copy files, and then we'll run our test copy. It's doing 100 records on each. That doesn't seem right. Yeah, it does not seem right at all. So it definitely had these correct there. Let's go ahead and blow away this directory again, and then we'll go here. What's wrong here? Oh, the BS. That's the problem. This is size. BS is 1. Oh, it says size here too. Yeah. Count 1. We'll just do count 1 on all of them. That makes it a little bit simpler. Alright. There we go. 1 record for each. 1 meg, 10 megs, 100 megs. Great. So then test, did I forget this? Yeah. So we got our stuff good here. If, or we can do a switch here. So we say esac case. Yeah, this thing here. Here, the var is gonna be $1, and the value will be, oops, please go away. The value will be create copy files. Great. Can I just do it like that and then do it like that? Kind of like that better. These guys, I'm going to say there. Then this is going to be echo usage. I forget the shell. Shell to echo to standard. There. test copy is hey, and let's say blah blah, create copy files. Okay, so now we have those. Oops, away. We also want to have a function here that will run the test. Run tests. So it's gonna iterate over all files in temp create, copy files. For each file, it will recompile the .c code, the copy, iterate over a range of values. This is buff size. If we look at chapter 4 copy.c 1024, 1024, 2048, 4096. For each file, to recompile copy code with -d, buff size equal to buff size, and then run the compiled C program with each temp. We don't need to recompile here. Iterate over range of, recompile the copy code. Then this will be iterate over all files there for each file. For each file, run the compiled copy. Great. And then here, if I look at chapter 4 make files, can I not open up that? Edit chapter 4 make file. Oh, come on. There we go. So ireflib. Copy C is going to be, let's say build copy here. This is going to be dot dot slash chapter 4 slash ref file IO, Output is build copy, and then we need our libraries probably. We're gonna need those, right? but we'll just let that build first. Okay, looks good. Let's go over here, quit out of that, get these things reorganized, jump to chapter 13, test copy, and then also have to add in here this function, which is run tests, or run tests, test copy, run tests. Okay, it does need that. Okay, so now we need to include the libraries. Chapter 4, ref, file IO, no, just ref, lib. There we go. And then I need the object files, which if I look at the make file here, oops, I don't want to make. Let's run make here, and then we can just include our local ref lib, and the object code goes here, I think. Where is it? These are the O files. They'll get built. And then these are binaries which have ref lib objects, which get put here. So I think what I'll do is say, hey, you're gonna get build ref lib star, something like that. Maybe, I don't know. Let's see. I do have the. Oh, this needs to be ref lib instead of ref lib. There we go. Copy no such file directory, so it's invoking this wrong. I'll just search for copy here, build copy. Great. Hey, look at that. Let's just run make once up here. Oh, run make once to ensure object lib. There we go. And we'll say, instead of going to dev null, that's the building here. We'll do temp. Copy files, dst files. Or we'll just say here, test. And we're going to time it as well. I don't care about this. that. That's fine. Here, let's go ahead and say echo buff size and what else? Oh, file name, which would be $file. So we echoed those. Yeah, that should be fine. Huh. And then this will just say tail N3. Oops. There we go. Why does that not work? Man tail N. Maybe 2. It's going to standard error, that's why. 2 and 1. Oops. And nope. The hell? Time whatever into 2 and 1 into dev null. What the hell? Oh. Maybe I have to do this as like a subshell, like this. Say, hey, time it. And then we're going to echo. I am. Okay, use a block. So say, hey, this whole block. There we go. I think it's a parentheses, not a like this. I haven't done the brace before, but I've done the parentheses before. There we go. We can just say grep real. Grep for real. And then here, we want to strip off the real. We don't want to have, we want to do -n here. We we strip off, say, awk print 2. We need a space too. So it's going to be like this. Maybe do dash slash t. Buff size slash t. File slash t. That. I think I need to say E here to evaluate those. There we go. Huh. So 1024 it's definitely going down with bigger buffer sizes. I think I need to change some of this 100K, 10K, 1K, and then we'll run create copy files, run tests. Oh, it's doing them in the wrong order there. Huh. Can I pipe this whole thing into sort numerically on column 2? Man sort. Column delimiter. How do I sort this output on call 2? Number 2 numerically. K 2 comma 2 dash H. Okay. 100K. I don't like this. I think what I want to do is list the files. Temp. So we test something? No. Copy files. There we go. I want these, the output of listing this directory to be sorted by the size of the number. So the output would be 1K, 10K, 100K, 1M, 10M, 100M. Okay, ls-1, then pipe that into sort human, km, okay, great, looks great. We'll put this into this. think I need to do it like here. Like that, yeah. Let's delete all this sorting stuff. What? For file and echo dollar file done. So those are definitely getting iterated over. So I have to say here, temp, copy files file. And then here, that's all great, but we need to say temp, copy files file. Is there any other use of file? Oops, this needs to be dollar here. Oops. Dollar here, not here. Okay. Just try it now. There we go. Does it really only take like 23 milliseconds? Maybe I need bigger files here. 1 gigabyte, 10 gigs. Create copy files. So if we look at 1K, 1K here, 1K here, it's going up as order of 10. 1K here is about the same because you're in the. Yeah, I imagine 1K is not going to change. Now we look at 10 gigs. So that was, with a small buffer, 10 gigs took about 700 milliseconds. Doubling that, reduce it slightly. Doubling it again, reduce it slightly again. I guess going from, yeah, doubling it again, reduce it tiny bit. Maybe our buffer sizes need to be bigger here. Oops. We'll take this last one off just because it's like huge. think I can indent all of these without issue. I don't think I need... do want to indent this more. I don't think I need this, because that'll automatically continue the line. And then this I don't know about. But we'll leave it there. Can do plot. Do I need to do like alright. What I'm going to do is comment out of all of this, delete that, make sure my awk is running at least. Okay, awk is running. And then this says to pipe it into this thing to sort stuff. Okay. And then we're going to pipe that into GNU plot. See what it says. And it says line 0, warning, skipping data file with no valid data points. I'm going to say, here is my script. Here is the output. Really don't want to mess with GNU plot. fuck? Okay, try it. Hmm. I don't think ChatGPT knows how to use GNU plot. So everything from the sort down to here. Oh, clear. The fuck are you doing? Convert times to seconds. Uh, so that's Gemini. In GNU plot, how do you read data? How do you plot data from standard in? Let's back out of some of these changes here. I want to go back to the first version that they had. Alright, which was this one. I'm just gonna give it the same prompt that I gave it here. See if it can use GNU plot. If not, we'll fall back to matplotlib. It got a plot. It just doesn't work. Export, copy to clipboard, paste. Time versus buffer. So we got buffer size there, time in seconds. Just has Alright, let's try this. It's such a waste of time. Sometimes AI is just the worst. Really, it shouldn't be too hard to plot all this. Well, didn't have any errors that time, but okay, no errors this time, but the plot didn't pop up on my screen. Set terminal, like that. Oops, terminal. What did it have terminal set to last time? QT, okay. Let's try that. Huh. GNU plot PE, GNU plot PE, title, X label, log scale, grid, key outside. PNG. Okay. Is there any PNG files here? Oh, there's a plot.png. Okay. Open plot PNG. Oh, that's great. Nothing there. Okay. Try this again. This is so annoying. This is so annoying. Okay. I am just super annoyed. Super, super, super annoyed. Um, these AI tools just like are not very intelligent, frankly. They're good at generating a bunch of slop. Oh hey, how's it going? Sorry, I was a little distracted there with this AI stuff. I'm trying to get GNU plot to plot a table of data. Um, yeah, I was trying to, hopefully, trying to get AI to just give me the GNU plot stuff, but doesn't seem like it's gonna work for me. Just run the test again here. Thanks for the follow. I think you're my first follow. I started doing these streams last week, I think, and basically, like, I'm focused on reading the Linux programming interface here. Michael Karisk. It's like a huge Unix tome, something I've been wanting to do for like years now, and yeah, starting to make some progress on it. So there's exercises at the end of this chapter. One of them is to time a bunch of different permutations of buffer sizes for this copy program. So when it's copying these files, it has different buffer sizes that it uses. and then also compiling it or running on different file sizes itself. And so I have that running here where the middle column is the file size. So I go all the way up to 10 gigs, from 1K to 10 gigs. And this is the buffer size that it's using. If we open up chapter 4 ref file IO copy.c, this is the thing here. You can see how they define buffer size here. And it's just basically like the user space buffer that's being used. It has nothing to do with like the glibc buffer, file IO buffer, or the kernel file IO buffers. It's an actual like user space buffer. In this case, it's being used for reading into, and then that buffer is handed off here to do a write. So it's a pretty simple copy program. Anyways, just I wanted to plot it to get a visual look at like how these things change. I kind of want to get GNU plot running because I have never used GNU plot before, and I hear really good things about it. I've used matplotlib a lot in Python, but I'm not really like a big fan of matplotlib. Let's see. I just want like a basic line chart. I don't want crazy stuff. Tutorials and guides. Maybe a line chart. Let's see if AI can give me a basic GNU plot program that can plot I guess this awk thing that they had, I might want to recover that because that did clean up the data a little bit. So I'll put that here. Delete the GNU plot thing here. There we go. So that's the awk. Oops. Wait a minute. That's the awk. And then that's the end of function. So let's fix the indentation here a little bit. Cool. So awk will then output it without milliseconds and stuff. So let's rerun that. You can see how that looks here. Okay. What I'm going to do is say, okay, this data is saved to a file whose contents are each, yeah, I'll just say doing that. Let's see what this does. GNU plot. How's this data.txt? Okay, so I need to write that out. So this thing goes into data.txt, and then I'm going to add a function here. It's called plot results. And I'm going to just tee this into build data.txt. Plot results. We'll then dump our GNU plot program here. And then we'll say plot. How do I do this? do I run that GNU plot code? Plot.gp. This will be build data, and this output will be build plot. Okay. Change mod plus exit, or no, you have to invoke it like this, I guess. Let me fix my indentation here, this is annoying. Okay. Make clean rm data.txt, and then we'll run our test copy run tests plot results. Build. So now we say plot results. That didn't look like it ran, but maybe it did. Open build plot. Hey, look at that. There is a plot going on here. Okay, can you give me a GNU plot program that will have a separate line for each, what is it? Separate line for each file size, the middle column. Okay, it looks about right, I guess. Plot GP. Okay. Plot results. Oh, I need to fix this data. Let's be build data. I'm just going to comment this out. Okay. Set terminal size. Okay, we'll use this since that's correct. Benchmark by file size. This isn't going to be block size, it's going to be buffer size. It's going to be time in seconds. Sure. File size is middle column. Colors. Split into arrays. Okay, let's try running again. Let's say cat plot.gp, and then we run it. So just feed that into the AI, see if it can figure it out. Okay. Alright, let's give that a shot. Hey, open build plot.png. There we go. Finally. It took forever. So basically when the buffer size is huge, the time it takes is like nothing. I would have expected more of a smooth kind of like dovetailing towards the end. Let's change our test. And let's add some more buffer sizes here. I think that's 1,000,000, right? What is the next value in this series? Okay, great. Oh, it's 16 million. So that means that this is 1,000,000 here, yeah. 2, 4, 8, 16, yeah. Okay. Let's rerun our test. Run test. And then plot results. And then open build plot png. So yeah, seems like as soon as you hit this 8 million size of a buffer, 8 million bytes, it's still not. So basically, for whatever reason, like there's this huge drop off here when you get to 8 million bytes being read and written at the same time. Which is interesting. I don't have an explanation for why that would occur. I mean, it makes sense that as you grow the buffer size, that performance will increase to a certain extent on every size, except for very small things. And it seems to be that's what you see. Like, okay, it's gonna, we have a doubling of file sizes, so or a 10x of the file size, so we're gonna see a 10x of the time it takes. Time is linear, this is logarithmic. Yeah. But it seems like something weird happens at 8 million. This looks normal, and then something weird happens here. Like, why is it so fast to... Hmm. 8 million. I mean, we're at 10 billion for the actual byte size. So we're not reading the whole thing. And remember, there's still multiple passes being done. Maybe we jack up the file sizes more and see if we still see this behavior on huge files. How much disk space do I have? DF, human readable. This is on TempFS, available. I only have 13 gigs. Oh no, that's not TempFS. This is the TempFS. I have 58 gigs. That's not enough. Okay, I'm not gonna look into it further. That was a nice little experiment though, and I got some experience with GNUplot. Basically, like, GNUplot's not really good at taking its data from standard in, or at least the AI couldn't figure it out. All right, it is noon time. I'm gonna finish off my matcha here. I think I'm going to 1. Yeah. So we're on the file IO exercises. Let's get through the rest of these since I'm not going very fast. Modify the OpenSys call to include OSync flag. How much difference does this make the speed of various buffers? That's going to be easy. It's going to trash the performance. I don't even need to do that, but let's go ahead and do it anyways. Let's go over here. Run tests. Yeah, I mean, these tests take forever now. And then plot results. So I'm gonna env build plot / plot to build plot 1. And then actually I'm gonna move that to plot 1.png, yeah. And then we'll say plot results, and then env plot build plot to plot 2.png. Oops, env to plot 2.png. There we go. If I open up, it's rm this plot by file size. Open up plot star.png. Does that not work? Open plot 1.png and open plot 2.png. Okay, so we got the sync results. The time in seconds went up slightly. Which one is this? Doesn't say. Oh no, it went up. Yeah, yeah, it went up slightly. It actually didn't like impact it that badly. I thought it would have been a much worse performance. It was interesting. Did I? Oh no, I did file perms osync. That's why. I need this open. I put it in the wrong location, that's why. There we go. So now let's rerun rm plot 2. I was gonna say that's like crazy. Run tests. There we go. And these might take forever just because it's like syncing everything. Try performing these timing tests on a range of file systems. Are the results similar? Are the trends the same when going from small to large buffer size? I'm going to skip that one because I don't really feel like spending the time to create those file systems. So now we do plot results, mv build plot to plot2.png, open plot 1, and open plot2.png. So plot 1's over here, plot 2 is over here. It's still not that bad. Oh. Vim copy.c. How is this open? Read only. Oh no, that's reading. We want to sync on writing. We want the out FD file perms. Yeah, so we had it right the first time. Because osync will be added to file perms. File perms then is used for the output file descriptor. And it'll sync everything. Try it one more time. Rm plot 2. I'm just going to rm build. Actually, we'll just make clean here. And then we'll say run tests. Are any of these exercises in the back here? 13. I got 13.3, 13.4. So timed operation of write bytes program provided in the source code distribution for various buffer sizes. I'm not going to do that. What is the effect of the following statements? File flush fp fsync file node fp. So fflush will flush the libc buffer into the kernel. Fsync will flush the kernel buffers. So everything will be, the effect of doing this will be everything that was in libc writes, they'll all be flushed to disk. This sequence of statements ensures that data written to standard I/O buffers is flushed to the disk. The fflush calls flush standard I/O buffer for fp to the kernel buffer cache. The argument given to subsequent fsync is the file descriptor underlying fp. Thus, the call flushes the recently filled kernel buffer for that file descriptor to the disk. Yep, exactly what I said. All right, let's, so we ran our tests, so ls under build, we have our data. So now, now plot results. And then I'm going to mv build plot2 plot2.png open plot2.png. Yeah, the delta is so minor. You can ask AI. I added osync to a program that has output file that is being written too heavily. The performance was only marginally changed by this additional flag. Can you explain that? I think it's my storage device characteristics, since it's an NVMe SSD. It's like super fast. Like nothing's actually being written to a, you know, hard drive platter or anything. So even with OSync, Linux still uses the page cache. When you write data, the kernel writes to the page cache. It then flushes the page to the disk. In modern storage, especially SSD, flush may be extremely fast. Yeah. Okay. Some file systems, like ext4 with journaling, may optimize osync writes. For example, odsync might sync only the data, while osync also syncs metadata. File system may combine multiple osync calls internally. Oh, maybe I need to like make my buffer size even smaller. Maybe that would like trigger this. I'm not gonna bother with it right now. Okay. Let's move on to the next one. Explain why the output of the following code differs depending on whether standard output is redirected to the terminal or a disk file. So printf, if I had more time. So in this situation, since we printf with a new line character at the end, if our standard out is a terminal, a TTY, it'll actually flush the buffer because of that new line. Whereas if it's a disk file, it won't flush the buffer. So you might see, so if this is written to a terminal standard out, then you would see if I had more time, and then I would have written a shorter letter. And then the reverse is true. If you're writing to a file, you would see the write come in first. I would have written a shorter letter if I had more time, because all the printf stuff is being buffered and not flushed until the end of the program. When the standard output is sent to a terminal, it is line buffered so that the output of printf call appears immediately. It is followed by the output of write. When standard output is sent to a disk file, it is block buffered. Consequently, the output of printf is held in the standard out buffer and is flushed only when the program exits. After the write call, a complete program counting the code of this exercise is available. Continue the code is available so and so. Blah blah. Okay, great. And then the last one is the command tail file prints the last num lines 10 by default of the named file. Implement this command using IO streams, IO system calls, lseek. I'm not going to do this. Lseek, read, but I'll think through it. Lseek, read, write, and so on. Well, you'd have to read the whole file in to memory, or at least have a buffer that's big enough to hold the last n lines. Like you could have, like, if n was like 10, you could have 10 different buffers, and as you're reading new lines, you just, go to the next buffer and kind of have like a ring buffer where you're overriding it. That might work. And then once you get to the end of the file, you just have the ring buffer that you have to output. I would use a ring buffer here. And you wouldn't need to lseek, except for lseeking to the beginning of the file. Yeah, I mean, this would be fun to implement. I'm not going to implement it just because I don't want to spend more time on those exercises. I already spent a lot of time on this one. But this would be fun to implement because you could have a ring buffer. So each, like, say your dash n was 10, that means the length of your, or the capacity of your ring buffer would be 10, and each element in that ring buffer, and by ring buffer I would just mean like a standard array, it would be pointing to the actual buffers, and those buffers, just for simplicity's sake, make them like fixed size, and basically, if your line is longer than that size, then good luck to you. But assuming the lines are within that size, just for simplicity's sake, then you would basically read into, say, the 0th element of that ring buffer until you hit a new line, and then you go to the 1th, and then you go all the way down, and then you would mod your way back to the beginning, and just keep on incrementing around and modding around, keeping track of where you are in the ring buffer. And then at the end of that, you would just add a +1 to the ring buffer index, mod, a modded +1, a modded increment. That would put you at the beginning of the last 10, and then you just output until you reach back to that index. And that would be the way I would solve that. And the only way I would want to improve on that, it would be to have a variable size array. Do some type of table doubling for the individual buffers, so that you're not limited by a specific buffer size. And doing all that heap allocated would allow for that dynamic aspect of the buffer size. Yeah. I'm curious how they implement tail now. But let's move on. File systems. Okay. In chapter, actually, let me commit my progress here. Let's go back here, get status, get checkout chapter 4, get status, get at all, vim, readme. We're done with chapter 13. Let's move on to chapter 14. And this is called file systems. Okay. Oops. mkdir chapter 14. rsync avzci. From chapter 13 to chapter 14. cd into chapter 14. ls/la. rm concurrent writes, plot star, test. Yeah, and then make clean, vim, clang.clangd. This will be chapter 14. diff cache, or let's add the readme, get add readme, get DC. So you have a readme change, that's good, that's good, all that's good. Good, good, good. Good new plot stuff, and then we have some binary files at the end. I don't like that. Vim test copy, Vim chapter 13 test copy, but I'll do it. Let's fix it. cd Vim chapter 13 test copy. This awk stuff has extra spacing. It's not necessary. Alright, get DC. Let's go up, make sure everything's good there. Alright, get CI, we'll say finish chapter 13. Oh, give me 1 second, I just need to blur this so I